Alright, so Physical Science 20, Unit 4, beginning light, Chapter 13. It's the first lesson on light, and on page 410 you can follow along. These notes are summaries, summary notes for what you would see in your textbook there. So read the textbook again, as I mentioned before. Read the textbook for the full story. These are the highlights. Okay? Alright. Sometimes science asks questions that seem obvious, but that turn out to have much more complicated answers than we thought when they're fully examined. What is light is one of these questions. This is because we've dealt with light in our lives for so long that we assume that our familiarity with it means that we understand it. So when we talk about what is light, maybe some of you guys think about, well, it's what makes the room bright so I can look around. Well, you might say it's what burns my skin when I'm outside too long in the summer, right? You might say, well, it's the heat that comes from those lamps, or from light bulbs. That's light. You have a familiarity with light. We know what light is. We know what darkness is, right? We know light, absence of light. But what is the nature of light? That's what physics and science tries to examine. What's the nature of light, and what is it really? So if we examine briefly a history of light, or at least the history of what light was thought to be. So here's some summary notes. Plato and Socrates were ancient Greek philosophers, and their original thoughts were that the eye itself actually emitted invisible light rays. So Plato and Socrates thought it's your eyes that create the light that you see. So Plato and Socrates thought that the eye emitted invisible light rays, and that those light rays reflected back to the eye in order to see the objects. So you have the eye emitting light particles, or light rays. Pythagoras came along, another Greek mathematician. You know the Pythagorean theorem, right, in math. He thought of light as particles that bounced off an object and then to our eyes. So he didn't think that it emanated from the eye, but that light somehow was coming from the object and then into our eyes, allowing us to see. So that's a little bit closer to sort of how we see things today. That was a big change. Aristotle, in the 4th century BC, thought that light traveled like a wave in water. And so there are competing theories about the theory of light, and of Aristotle, who was a pretty important scientist or natural philosopher, thousands of years ago. What he thought was that light was like a wave that traveled through water. Okay, very interesting. Not particles, and as you notice here, light rays, light particles. Aristotle came along and said, you know what, that doesn't really fit. I think it's more like a wave in water, something that's a little bit more fluid, right, instead of rays or particles, like actual bits of things. Leonardo da Vinci in the 1500s, he agreed that light traveled like waves, and he had and that it had some wave-like properties. And more importantly, da Vinci thought that it was a wave very similar to sound, that light and sound were very, very similar. So there's another thing that was kind of added on to the nature of light, what they thought nature of light was. In the 17th and 18th centuries, the debate between whether light was a wave or a particle began to be able to be tested. So again, what we have is competing theories. We have light as a wave, and then originally light as a particle, rays or particles. So this was a debate, and in the 17th, 18th century, these ideas began to be tested. Isaac Newton, you've all heard of him. He developed a very strong theory of light as a particle that explained the bending of light, that's refraction, the reflection of light, and its color. So again, Isaac Newton, very well respected scientist of his age, and basically whatever he said was the truth. Isaac Newton, everyone kind of believed Isaac Newton, and he was very well respected. And so he said, you know what? Here it is. Light behaves like particles. We have to think of light as little bits of things that are flying around. Christian Huygens showed mathematically how a wave waves could demonstrate the phenomena that light exhibits. Plus, his theory also explained diffraction. So Christian Huygens more support for a mathematical explanation of how light works. In 1801, Thomas Young does the famous double slit experiment, showing that light definitely has a diffraction pattern. So he was able to diffract light, and light, as it traveled through an opening, just like the properties of waves that we studied in the last section, how when waves travel through an opening, they sort of bend and they diffract. So he showed that, light can do this same sort of thing. So light as a wave. Well, that upset the theory again. Now we're back to wave theory, right? Augustin Fresnel develops a comprehensive mathematical wave theory of light. So now we're back to waves. Newton says particles. Now these guys are coming along saying, no, it's back to waves. There's this real battle, hey? And this is my favorite, of course. James Clerk Maxwell, a very famous Scottish physicist. I must say, I am not as famous, but I'm Scottish as well. And being that my last name is Maxwell, we're probably related. Just saying. Probably. James Clerk Maxwell. Actually, my dad's name is James Lloyd Maxwell. Interesting, isn't it? James Clerk Maxwell developed very robust mathematical formulas that explained how light was formed due to electrical forces acting within the atom, and which produced a wave called electromagnetic radiation. I'm going to give you a little bit of time to copy this down and to go over this again. And frequencies, exhibited from 10 to the 1 to 10 to the 25 hertz. And visible light is around the 10 to 15 hertz, okay? So just take a minute to copy this down and read through this next section. Light is just a small part of this frequency of radiation. Radar, microwaves, radio waves, lasers, that sort of thing. This has all been developed based on this theory and based on the math behind electromagnetic radiation. So obviously this is pretty good support for light being a wave. I mean, it's caused all these things to be developed and invented and introduced and make our life all easy. And these formulas are pretty robust, explain pretty much everything. So it's a wave, right? Well, unfortunately, light also behaves as only a particle can sometimes. This means that scientists have had to say that we truly don't know the exact nature of light. We might call it a wavicle. It's not an official term, of course, but it's fully particle and fully wave at the same time. So even though we don't have a really full understanding of what light really is or the nature of light, whether it's a wave or a particle, the neat thing is that we have a very good idea about how light behaves and how it affects things. And so we can really look at it from both sides. We can look at it as a wave and we can look at it as a particle. And it helps to explain a lot of things, it helps to predict a lot of things, and it helps to invent a lot of things. So it's kind of like we're getting different perspectives of the same thing. And even though those perspectives seem to collide, even though they seem to be opposite perspectives, they're just looking at the same thing from a different angle. Okay? So wave, light theory, it's okay. We don't have to have one over the other, really. Okay, so the next section is the speed of light. So let's talk about the speed of light, and this is going to be page 412, starting your textbook. How fast is light? Well, we know that it's faster than sound, right? We talked about our unit on sound, and we talked about the fact that you see lightning before you hear it, right? Or you see lightning before you hear the thunder that accompanies the lightning. If you're watching a baseball game and you are, in the outfield, you see the bat hit the ball before you hear it hit the ball, slightly. If someone is clapping or if someone is shouting, all right, what you hear will be a little bit behind what you see happening. But light is not instantaneous, okay? It's not instantaneous. It does have a definite speed. There were many reasons to think that light was instantaneous. for a very long time just because it was so very fast. Also, you can't see it move in our everyday life, so people thought that light sort of just existed. It's not that a light beam traveled and it actually took some time. But when we observe things that are really, really far away, you can start to notice that there is a lag or a delay that is produced by light traveling. A Danish astronomer, Olaus Rømer, noticed that while observing eclipses of the moons of Jupiter, so when we're talking about things that are really far away, like the moons of Jupiter, yeah, pretty far away. That's a little bit further than a mile or two. We're talking millions of miles, right? So he noticed that when observing the eclipses of the moons of Jupiter, at one point of the year when Earth was on the opposite side of the Sun, so this means that Earth is quite a bit further from Jupiter and its moons at one point of the year than it is at another point of the year, he noticed that it actually took longer for the light to reach Earth. According to his calculations, he was supposed to see the eclipse at a certain time, but he noticed that when Earth was quite a bit further away from Jupiter, that those times didn't line up. And so he kind of had this idea that, you know what, there's a difference in the time. I wonder if that's the difference in how long it takes the light to get to me. So when Earth was on the opposite side of the Sun, it took longer for the light to reach Earth. And therefore the eclipses appeared later than he had calculated. When Earth was on the same side of the Sun as Jupiter, the eclipses appeared earlier. And there is a good picture on your textbook, page 413. And I'll just take a moment just to kind of draw this a little bit for you. So when Earth, here's Earth, was over here, and Jupiter was here, and its moon was here, there's a certain distance there, right? But when Earth is, the other side of the Sun, over here, and it's not a perfectly spherical orbit, right? The Sun is not right in the middle of this orbit either. So as Jupiter moves, let's say Jupiter comes over here now, you see how this distance in green is quite a bit longer than this distance in black right here? And so that's the difference that Rømer was talking about. And he noticed that, hey, it takes longer, like the light has to travel further. And because my calculations, they're a little bit off, I wonder if that's because of the difference in the speed of light. And of course, through experimentation of him and others, we've come to the agreement in the scientific community that the speed of light is this fast right here. This is the speed of light. It's 3.00 times 10 to the 8 meters per second. That is 300 million meters in 1 second. That is pretty fast. That is pretty fast. It seems almost instantaneous, doesn't it? I mean, when we're talking about switching on a light switch here, as soon as that bulb comes on, it seems like the walls light up instantaneously. Well, guess what? From the light bulb to the wall is such a small fraction of this distance right here, right? It's going to take far less than a second. It's going to take like a nanosecond, and you're not even going to notice it, right? So 300 million meters per second. I think that really in 1 second, a beam of light, if you flashed a flashlight and that beam of light was able to travel all around the Earth, in 1 second, that little flick of your flashlight would travel 7 times around the Earth. That's how fast it is. So super, super fast. If you were to flicker of a candle or of a lighter or something, right? That little flash of light, that would travel almost 7 times around the Earth in 1 second. So it's really, really fast. I'm going to remind you that I'm going to get you to do some questions, but remember that velocity equals distance traveled over time taken. Okay? So you need to remember that velocity is the distance traveled, the total distance, or the change in distance, divided by the change in time. And so using the speed of light, and you know what? The symbol for speed of light is a lowercase c. So when you see the lowercase c in your calculations or in your examples, then you know that that is the speed of light. Please remember that this unit is in meters per second, not kilometers per second, not meters per minute, meters per second. So when you're calculating time using the speed of light, this is in meters per second. Guess what? The time is going to be in seconds. What's the distance going to end up to be when you do this calculation? Meters. Okay? If you have to convert meters to kilometers, you can do that. If you have to convert seconds to minutes or days, you can do that as well. But notice that in this basic formula, you've got the velocity of speed of light is in meters per second. That's the typical unit of speed or velocity that we've used. Okay, so complete questions 1 and 2 on page 414, please, and you can have the rest of the class to do that.